when we're burning hydrocarbon fuels, we use a little extra air for that combustion process for a couple of reasons. One is for safety, to do everything we can possibly do to ensure complete combustion, that all the fuel is used up. And the other, of course, is economic reasons. We're buying that fuel, and we want to be sure we get our money's worth for what we're buying. And so this module is about excess air. How does that reaction equation change when we recognize that we're using a little excess air, sometimes a lot of excess air, to complete our combustion process? So let's have a look, see what level of complexity we're going to add. So as we talked about last time, there's two primary reasons for using excess air when we're burning any hydrocarbon fuel, C sub M, H sub N. One is to do everything we can possibly do to complete the combustion process, and for safety reasons, not leaving any combustible fuel in the exhaust, where combustion or a fire might happen where we don't want it to happen. So, for example, fuel oil combustion. I tried to give some examples of open systems and closed systems combustion. Now, in Chapter 13, I can only think of one example problem in the book that you may or may not be covering in your class, where there is a closed system. So up here in the upper right, so recognize that in internal combustion engine, that combustion process is going to take place in a vessel, piston and cylinder, where the air molecules and the fuel molecules are mixed together, and there might be a spark, or in the case of the diesel cycle, the combination of pressure and temperature within the piston and cylinder will initiate that combustion. Now, in Chapter 13, nearly all of your problems and all of the examples is looking at fuel and air combined in an open system, steady state, steady flow. So I've tried to depict this from a commercially available, this would be a fuel oil burner that might be used in a household furnace, where here's the fan, and the fan is delivering air up into a mixing chamber. The hydrocarbon fuel, like perhaps number 2 fuel oil, heating fuel, that's an awful lot like diesel fuel, is admitted through a pump. Those two are combined in the open system, and so the exhaust products and the heat is released and so what's coming out of here is going to be the exhaust products. And I've tried to grab a picture of what you would see in a fuel oil combustion, steady state, steady flow, open system process. So you can see the burner, here is the flame. Notice here how this flame is very yellow, and that's the way we can detect whether our fuel is a liquid fuel like diesel fuel or gasoline, compared to gaseous fuels like propane and natural gas, where typically you see very much of a blue flame. And I am no expert in combustion. I am barely capable in this introductory level, so I can't go any further in explaining the whys. I can just recognize that what we see with our eyes is gaseous fuels, natural gas, propane typically is a blue burning flame, and fuel oil combustion typically is a yellowish type flame. Solid fuel combustion typically is observed in large steam generators or bonfires out in the backyard, fire pits, things like that. But in the industrial area, you're going to see solid fuel combustion in a very large steam generating unit like I've shown here. This is an example of a fluidized bed steam generation boiler where hydrocarbon fuel is augered in through fuel chutes. So there's an auger delivering, in this case, either coal or wood chips augered into a chute. And that fuel is going to then go into this sort of bubbling bed, where air is admitted underneath this bubbling bed. Okay, that's where the combustion is happening, and then the exhaust products are coming up here through this furnace. Combustion is continuing in this very large area, and then the exhaust products are passing over top of these the superheating tubes, where steam saturated vapor is then increased temperature into superheated vapor. And then, of course, the exhaust is coming back around here. It's heating up boiler feed water since the exhaust has gotten colder, and then out goes the exhaust products up to the exhaust stack. So that's a great example. It's a good look at a fluidized bed boiler, solid fuel combustion at the industrial level. Okay, and so now getting back to problem solving and theoretical air. So theoretical air is the same as saying stoichiometric air. Theoretical air means use the stoichiometric reaction equation in setting up your equation. When you just say theoretical air, it's the same as saying 100% theoretical air. That's the same as saying set up your stoichiometric equation. So here, the theoretical air is going to be right from the previous module, where you've got a fuel, C sub M H sub N. You can set up kind of your little cheat sheet here that I do. I'm going to have to admit, I set up a little cheat sheet and see that I've got B is going to be equal to M, C is going to equal to N over 2, here's C, and A, the number A, is going to be M plus N over 4. And so I just jot those down. That is my stoichiometric equation, burning air. Remember, nitrogen. It's just along for the ride. Okay, so that's a setup for 100% theoretical air, or the stoichiometric equation. Now let's move on to burning with excess air. Okay, there was theoretical air, and oh, here we go. And so remember, if we go back to our basics, we've got our fuel, CH4, we've got our oxidant, which is air. So we're just using a little example of methane, CH4. And so with excess air, we've got some question marks to answer. Okay. Oh, I'm sorry, this is stoichiometric air, a little bit of a reprise of the previous slide. So you set up your stoichiometric equation using your little cheat sheet, 100% theoretical air. I put this in to set up the next slide, so I'll have to apologize for sort of doubling up. So that was the stoichiometric equation. Now we move on to excess air. The reason I put that in is, remember this A here. That A is a value that depends on M and N, okay? And that's sort of the stoichiometric type factor that's needed to balance the stoichiometric equation. Now for excess air, we're going to add another factor in our air part of our reactance equation, and it's going to be 1.XX. And so do you see that if we do this, you see that we're going to have some oxygen left over. And so in my slide, I've mentioned exhaust products, do the algebra. So I'm not going to show the algebra right here, right? Because you have the ability to do the algebra if you know what A is, and you will, and if you know what 1.XX is. You just do the algebra, and your exhaust products are going to be CO2, H2O, nitrogen, N2, it's along for the ride. And do you see that because of the algebra, you've put in a little excess moles of oxygen. And so in the exhaust products, you're going to have an extra constituent, O2. O2 is going to be in there. And now by example problem, I'm trying to give you an idea of what does excess air mean? Well, when this factor is 1.00, that's theoretical air. That's 0% excess air. That's stoichiometric air. That's 100% theoretical air. 1.00, that's the stoichiometric equation. Now, if your factor here is 1.05, that represents 5%, 0.05, 5% excess air. 1.1, that's 10% excess air. 1.5, that's 50% excess air. That might be something like a bonfire, okay, that's burning in your backyard. Or even if you go all the way up to 2.00, instead of 1.xx, you've got 2.00, that's 100% excess air. And so it's my hope, instead of giving you a formula, I'm trying to give you by example to get into your head. Do you see the relationship between this factor and the percent excess air? That's my hope of what you absorb from this slide. So 1.10 in this factor means 10% excess air. I'm going to try to drive this home a little more, if you don't mind. Here's my combustion equation. C sub M H sub N is my hydrocarbon fuel. 1.XX, that's my factor for excess air. A, that's just a number that you get by balancing the stoichiometric equation. So I'm going to try to tabulate so you can see with your eyes, what does this stuff mean? What's the relationship between this factor, 1.00, 1.05, 1.10, et cetera, the excess air percent, and the theoretical air percent. Okay, so let's do the, instead of doing all of them, obviously, let's do 10% excess air. So 1.10 is our factor. That means 10% excess air. And that's the same as meaning 110% theoretical air. I hope that helps get you a common sense feel for the difference between stoichiometric air, theoretical air, 100% theoretical air is the same as stoichiometric, and excess air. 0% excess air is stoichiometric. Hope that helps. The next definition in your chapter 13.1.2, modeling combustion air, is a very commonly used ratio that we use out in industry, in commercial analyses of fuel and air and that type of thing. The air to fuel ratio that we simply call AF, air to fuel ratio, and it is defined as, in your textbook, the mass of the air divided by the mass of the fuel based on the masses that you get from the combustion equation on the left-hand side. The fuel, that's the fuel, that's C sub N, H sub N, the number of kilograms of that in your equation. The air, that's the oxidant, that's the kilograms of nitrogen and oxygen moles in your equation, but it's kilograms per kilogram. So the air to fuel ratio, it's not exactly dimensionless. The air to fuel ratio is the kilograms of air for each kilogram of fuel. So get in your head, not necessarily a formula. Air to fuel ratio is a mass ratio. And you're going to be asked to determine that in a number of your homework problems. Perhaps in one of your homework problems, you're going to be asked to find the equivalence ratio. Now, I'm going to have to tell you that I was not familiar with this term as an undergraduate. As a graduate student, was not exposed to it. Even when I was working for a living in industry, we did not use equivalence ratio in the work area that I was working in. But it is important. I believe in the internal combustion engine area, the equivalence ratio is important. So here's the definition of equivalence ratio. The equivalence ratio, it's a little complex. It says it's the fuel to air ratio of the actual combustion divided by the fuel to air ratio for stoichiometric combustion for 100% theoretical air. So here's what this means. I think I've written a better formula than your book has. The equivalence ratio, ER, is the fuel to air ratio. Remember, that's 1 over the air to fuel ratio. It's the ratio, it's the reciprocal of that. Fuel to air ratio actual divided by the fuel to air ratio for the stoichiometric combustion equation. So you've got to sort of do two computational parts to get the equivalence ratio. And you say, so what? So what? Well, here's what the so what is. An equivalence ratio of 1.0 means that you're using theoretical air. You're satisfying the stoichiometric equation because this ratio would be equal 1. In the internal combustion engine business, though, an equivalence ratio of less than 1 means you're running lean. We've heard that term, haven't we? You're running lean. You're running too lean. That could mean that your exhaust gas from your internal combustion engine is very blue and it's got some fuel left in it. It's unburned fuel coming out of your exhaust. That's lean. I'm sorry, I said that wrong. Lean is excess air. If equivalence ratio less than 1 means you're running lean, that means that you are putting in more air than needed. So you're running lean. I would expect complete combustion, hopefully, from a lean mixture. Okay, whew, I had caught myself. An equivalence ratio greater than 1 means you're running rich. Fuel rich. Okay. And you've heard that term, right? You've got a rich mixture. That's the situation where you probably see a very blue smoke coming out of your exhaust, meaning that you've got unburned fuel coming out of the exhaust. That would be rich. That's fuel rich. And potentially that could be a dangerous situation, right? So when you're running fuel rich, in my limited internal combustion engine experience, I believe that is potentially more dangerous than running lean. Sorry, I did my little blunder on my yellow text box. Okay, and so do you see that in common practice, we're generally adding excess air in our open system combustion processes when we're adding fuel and air in a steady state, steady flow, 2 inlets and 1 outlet situation. We're usually running excess air, and it does add an additional level of complexity, but I believe it's a small level of additional complexity as you're going through your combustion analysis. And so don't be scared away from excess air calculations. Gosh, I hope that helps. Sorry for my rich and lean blunder, but these things do happen when you're going live. And I hope it helps you and helps you gain some confidence when you're asked to do these combustion reaction equations and provide the combustion reaction equation for excess air.